Question 9. Figure 4 shows a sketch of the curve with equation x squared subtract 2xy plus 3y squared equals 50. So we have a diagram there showing a bit of an elliptical function, sort of at an angle. We've also got the y-axis labelled north and the x-axis labelled east. Part A asks us to show that dy by dx equals y subtract x, all divided by 3y subtract x. So when we're differentiating implicitly, it means that we haven't got x or y explicitly as the subject. They're all mixed up. And we just need to remember that when we differentiate it with respect to x, any function of x we do as normal, but any function of y, we just need to remember because of the chain rule, it's a function of x. So we differentiate it, but we just have to multiply it by dy by dx afterwards in practice. Now we've got negative 2xy in there, and that's two functions multiplied together. So I'm just going to remind ourselves of the product rule. So if you differentiate two functions multiplied together, it's u multiplied by the derivative of v plus v multiplied by the derivative of u. So let's start differentiating our function. So I'm just going to write out our function again. So let's differentiate this. So x squared will become 2x. And then we got our first issue, we've got this negative 2xy. So what I'm going to do is I'm going to use the product rule. We've got that written above. So I'm going to label u to be negative 2x. And I'm going to label v to be y. So u dash is going to be negative 2. And v dash, so if you differentiate y, you get dy by dx. The derivative of y with respect to x makes sense, is dy by dx. And now we can use the product rule. So it's going to be negative 2x times dy by dx. And then plus, so negative 2 times y. Now if we differentiate 3y squared, we're going to get 6y dy by dx because it's a function of y. And then the 50 on the end, if you differentiate 50, it becomes 0. So we're going to keep all the dy by dx as one side. Now I'm looking up here. We're trying to get 3y minus x on our denominator here. So I'm actually I'm going to keep the 6y dy by dx, subtract 2x dy by dx over on the left hand side, and I'm going to move over the 2y and subtract 2x to the other side. We can now factorize, so we get dy by dx multiplied by 6y subtract 2x is equal to 2y subtract 2x. We can now divide this over, so dy by dx is going to be equal to 2y subtract 2x, all divided by 6y subtract 2x. Now we've got fractions with a common factor of 2, so I can divide everything by 2, and we get y subtract x, all divided by 3y subtract x. Now if we double check, that is what we wanted. So happy days, we have completed part A. Part B, the curve is used to model the shape of a cycle track with both x and y measured in kilometers. The points P and Q represents the points that are farthest west and furthest east of the origin, so you can see that in the diagram. Using part A, find the exact coordinates of P. So this point over here, P, so we're trying to find here. So we need to consider the gradient at point P. Now I think for a stationary point that's a bit more obvious. So if you're trying to find the furthest north point, which is actually what we're going to be doing part C, that's where you've got a stationary point. So here, your furthest north point, that's where dy by dx would be 0. You've got this flat line. Here the gradient, we could say, well, maybe is the gradient here, well, it's so steep, is it infinitely steep? So we can't ever put something equal to infinity, but that's almost what we're implying here. If we were going to be equating the gradient to 0, if I say I put this up here as 0, that means that eventually, effectively, I'd be making the numerator 0. So if we were going to be equating the dy by dx to infinity, the way that you would have something approaching an infinite gradient would be if the denominator was 0. So remember, you're not allowed to divide by 0. But the approach here is what we're going to do is we're going to create an equation by making the denominator of our fraction 0, because that would give us something approaching this infinitely steep gradient. So because we want to find the furthest west point P, I'm going to say that dy by dx is going to be approaching infinity. Never put equals to, because you can't be. And that will imply that 3y subtract x will have to be equal to 0. And that from that we can create this equation 3y is equal to x. That means that we can do simultaneous equations. So we've got an equation 3y equals x, and we've also got our original equation. So I'm going to sub in x as 3y in here. So our equation is going to become 3y all squared, subtract 2 times 3y multiplied by y plus 3y squared equals 50. So this is going to give us 9y squared subtract 6y squared plus 3y squared is equal to 50, which means we're going to get 6y squared equals 50, which means y squared is 50 divided by 6, and so we get y is the square root of 50 over 6, which would be the square root of 25 over 3. We've got to remember when we use a square root to solve an equation, we need to put a plus or minus. So we could put this in the calculator, but I quite like to do it ourselves. So the square root of 25 is 5, and the square root of 3 would be root 3, plus or minus. So that means that it's 5 root 3 over 3 if we rationalize it. Now if you look at p is the negative version of this. So that means what we're going to do is we're going to take our y here to be negative 5 root 3 over 3. Our x is 3 times y, so we'd multiply that by 3, they cancel out. So what we're going to get is our point P is going to be negative 5 root 3, negative 5 root 3 over 3. In part C, we need to explain briefly how to find the coordinates of the point that's furthest north of the origin, but we don't actually need to calculate it. So the point that's furthest north will be up here, and that's a bit like a maximum point. So the key thing here is that dy by dx, the gradient, would be 0. There's also this other point down here which would also have dy by dx here at 0. So the point furthest south. So what would we do? So let's explain briefly. So the first thing I would do is I would equate dy by dx to 0. So if we did this, if we equated dy by dx to 0, what that would do is that would actually create the equation y subtract x equals 0, the numerator, and then we could say that y equals x. We would then solve y equals x simultaneously with the previous function. So we would solve simultaneous equations with y equals x and the original function. Would that be enough? Well, actually, what we would then need to do is just make sure, because there's actually 2 possible solutions, so we'd have to take the positive solutions for x and y. So that's 10 marks banked for question 9.